Okay.
Well, I don't know if we did anything.
Can we change it?
Yeah, we could just like.
So you want to go down a little?
Can we change it?
Oh no, yeah, because he's the projection. Yeah, that's good.
Yeah. So it's just going to be delayed on this one. So.
Well, yeah, because I'm
Yeah.
the live that way.
So. Making sure that.
You're the. Perfect.
So does the camera look like you can see everything?
Yeah. I mean, it's a little fuzzy just with the distance and how Mac camera works, but I mean, you can get the whole field of it. You're getting from that end of there to about 3 or 4 feet beyond that. So.
Oh, that's cool.
Yeah. So I don't know where. No, but it should be. There we are. So it's as good as you're going to get.
I've got that one. So that's
You want to look at the chat on here? Or do you want? Do you want to read the chat and then let me do the question for Ben? If you says like, hey, you guys want to answer questions, then you can read them all.
You said another. I think it's an awesome opportunity.
so people ask questions.
Yeah. So these people are live right now. So we've got 13 people watching.
So they want some.
Yeah, they can see.
Awesome.
Wait again, more? I think so.
How are you? Good, how are you?
I'll see him out there.
I don't know what you're doing. You gonna do it later, or do you want me to grab you some pizza?
She'll probably be gone.
I can grab you.
Do you have a link for this actually? Do you have a link for this? I was gonna send it to my Brandon.
Yeah, that's all I'm trying.
I couldn't go back in the line. Look at the line.
Yeah.
Michael, I want to make sure you're okay, man. I haven't seen you in a minute.
Yeah, I actually love the mic.
Oh, okay.
Yeah.
Oh, did you get a tattoo?
Yeah, I've had it for a while.
Oh, okay.
Let me just set this through.
Yeah, go for it.
Probably needs to. Hello, everybody. Hello, what a turnout on winter break. Thank you. Thank you all for coming here to listen to Ben Derby's presentation. We have students, staff, family members, friends, a great turnout. So I'm really pleased to introduce Ben Derby. He has been a student in my group since fall 2015. Ben, I'll let him add more whatever he would like to add about his background. But he grew up in Syracuse, New York, which I'm told gets more snow than Ann Arbor, and then came to a warmer place here. Before that, he got his bachelor's degree in physics from American University, so it was a transition to engineering and materials, and he had to go through all the dislocation stuff, dislocate himself to learn about all the material science of imperfect materials and making interesting materials. He spent quite a bit of time in New Mexico to get away from the Michigan gray skies. He would go there to do experiments. And throughout his thesis, he has published a number of papers. He has won a number of awards, and he is looking to graduate end of this term and go do a postdoc in New Mexico. So with that, I would like to hand it over to Ben to talk about his dissertation research. And the format is that after that, we will have questions from the audience, and then the audience will be excused, and then there will be questions from the committee. I would like to introduce the committee members. They're all somehow scattered to this, segregated to this side. Professor Michael Latzman, Professor John Heron, and Professor Liam Chi. So thank you for your time. Thank you for coming here on Twitter. All right, please welcome Ben.
Sharing one of my favorite quotes by a material scientist, actually introduced to me by Professor Misra. It says that materials are like people. It's the defects that make them interesting. And today I'd like to share with you and tell you about a particular kind of defect known as interfaces, and share with you a story. Let me get my presentation below here. Share with you a story about engineering bicontinuous interfaces in a novel way to form thin films with enhanced mechanical performance. So throughout this story, we're going to run into a few scientific challenges that I hope together we can resolve. So thin films might sound foreign to you, but in fact, we use them every single day, whether you have a cell phone, a watch, or use drill bits. Thin films as a class of materials allows us to combine bulk properties in materials with the surface properties of other materials. So whether we're talking about protective coatings, microelectronics, optical coatings, decorative coatings, or even tribological or hard coatings, just by applying a thin layer of material onto another, we can enhance the properties of those materials. Now, the performance of thin films in all of these applications depends strictly on how they're designed on the nano scale. And we'll see this is the crux of my story that we're going to share with you today. So keep that in mind. So how thin films are typically engineered or designed is through a process known as physical vapor deposition. And but what the name implies, this my video is not going to load here. What the name implies is that we're actually vaporizing a material in a chamber, and it allows it to condense onto a substrate, another material, in very thin layers, in atomic layers, to grow a thin film material. Why we use this process is that PVD allows us to control certain aspects of the microstructure, namely the shape, the spacing, the crystallography, and the chemistry of the thin film, which again plays into the properties in those applications I described before. So typical thin film architectures look something like this. On the left, you have a fairly simple case where we deposit a material onto a substrate, and it might have some grain structure that we can describe with one length scale D. That's the grain size of that material. Another material is actually a composite of two or more materials that we've layered sequentially in a multi-layered stack. We can also describe this with one length scale, lambda. And this is the bi-layered length scale for that material. Now, this material on the right, this nanocomposite, is actually a very interesting material as it has interesting mechanical properties. I'll tell you why right now. So if we take a material, say copper in the bulk, which has a hardness of roughly 300 megapascals, we take another material, niobium, which has a higher hardness, you might think that if we combine these two materials in a composite, the hardness would be some value in between those. But in fact, if we make a thin film material at some layer thickness, say 40 nanometers in this stack, it has a high hardness, not between these two values, but much, much greater. Ultra high strength in this thin film architecture. In fact, that lambda parameter, as we decrease it in this plot here, which you can see going towards the right as a measure of hardness, you can see that as we decrease the lambda value for that nanocomposite, we increase the hardness of those materials. So you might be thinking, well, that's great. We have ultra high strength in a material. So what's the problem? Well, if we load this sample up in compression, so we make this micropillar and compress it down, deform it, it actually has these ultra high strengths, but it fails very suddenly like a brittle material. And the reason for that is this is the post-deformation sample. We can see that the plastic flow that we've created during deformation localizes into a single region in the sample known as a shear band. And that material fails very suddenly like a brittle material. So the question we ask in these nanocomposites, while we have the high strength in the material, they behave like a brittle material. Could we design a nanocomposite instead that's highly deformable but still has that ultra high strength in the material? So we saw this as a design problem. So previously we had these multi-layer stacks that fail suddenly. This is a TEM image of that sudden failure after deformation. And what we saw is if we could possibly design a structure that instead looks like this, which you notice has interfaces not in 2 dimensions anymore, but in 3 dimensions, we can possibly distribute strain much more uniformly in the sample during deformation. And so the question that we ask then is, how do you engineer a material that looks like this? Well, in fact, this structure here looks like, to some of us in the room, a phase-separated alloy, a phase-separated structure. And to a material scientist, phase separation looks something like this. We take a homogeneous alloy of a certain material combination, we give it some energy, for example, temperature, and we can phase separate that alloy into 2 distinct domains. In this structure, the yellow and blue domains. We can actually design very sharp interfaces between those phase boundaries. Now, I said this occurs for very specific combinations of materials. What are those combinations? Well, if we look in our thermodynamics textbook, those are materials with high heats of mixing. These are materials that do not like to mix. For example, the copper-moly system. This is a copper-moly phase diagram where you can see it maps out temperature and composition, and you can see that this system is very insoluble. An alloy or thin film that looks exactly like this on the right. So you can imagine doing this a few different ways using physical vapor deposition. So take, for example, we have a copper target and a moly target. We condense that onto a substrate. We might form a homogeneous alloy like I described before. We deposit an equal amount of those two materials. We could heat it up, and we could form this 3D bicontinuous-like structure that I described before. We've actually seen this in the literature. So this is an example of a co-deposited copper tantalum system where the alloy at room temperature is homogeneous in the atom probe study here. We give it some temperature, and you can see that by adding temperature, we form this bicontinuous-like morphology for the copper and tantalum system. So you might be saying, well, that's great. Why don't we just copy that processing route? Well, the problem is that it's kind of cumbersome. We have to take the alloy out of the chamber, we have to heat it up, and the resultant morphology is actually the same every time we do it. So we're actually limited in the number of morphologies that we can achieve using that processing route. So we thought, well, why don't we change it up? We can actually add energy during deposition by heating the substrate. So why don't we add temperature while we're depositing the material? So we thought that in that case, we might be able to expand the number of morphologies that we could deposit using this processing route. We've actually seen this in literature as well. So actually led by one of my committee members, Dr. Michael Atzman, led a study where they co-deposited aluminum germanium onto a heated substrate. And what they found was a bicontinuous-like morphology. And here are the resultant morphologies. So you can see the aluminum-rich and germanium-rich phases highlighted here. And what they did was they varied the substrate temperature during deposition. What I hope you can point out here is that the sample coarsens as a function of substrate temperature. The domain size of the phase-separated architecture actually grows as a function of temperature. And that was one of the major findings of this work, is that we could actually control that phase separation process using the deposition conditions. So they actually tried to model this system analytically using one initial assumption, and that is that everything that's evolving, the concentration, is happening on the surface, the growing film surface. As in, the deposition time and temperature are such that no bulk diffusion is happening during deposition. And this is what it looks like here in this video. Oh, man. Uh-oh. That's too bad. I'll show you at the end. So hopefully, this actually is a video that describes the phase separation process onto a substrate. What this video would actually show you is that the samples, the atomic atoms that deposit onto the substrate, actually diffuse along the concentration evolution over the course of the deposition. And so what they used was they used a Kahn-Hilliard formulation to describe this process, where they mapped out the concentration evolution over time as a function of the deposition conditions, namely the surface diffusivity, so how fast these atoms are traveling on the surface, the deposition rate, how fast we're adding material to the growing film, and the surface layer width, so how large is that layer that's actually evolving in concentration. So they idealize a structure that looks like this. So this is an alpha and beta rich morphology where you can see those phase separated designs at some length scale R. So that measures the domain size of that structure. And what they saw, what they concluded, is that that domain size R is a function of how far an atom can travel on the surface before it's buried by the next incoming deposited layer. And you could actually recognize that these two things are proportional. This actually, on the right-hand side, describes how far an atom can travel in diffusion, just like the Einstein relation. So they describe the surface interdiffusion length depending on the deposition conditions, namely the temperature, which feeds into this D variable, the surface diffusivity, and nu, which is the deposition rate, how fast we're adding material to the system. So this model was actually later improved upon by a group at Ohio State led by Yunzi Wang, which just saw this equation just a little differently. They saw this equation as a competition between two different rates. The first rate being the rate of phase separation, and the second being the deposition rate of during growth. And so the competition of these two rates can not only determine the size of the domains, but the direction of phase separation during thin film growth. And you can see that as a function of rho, this interdiffusion length, we can change the morphology or the direction of concentration modulations in the sample. So you can see these red and blue phase, this is a two-phase material. You can see at high surface diffusion length, we have this lateral concentration modulations. And as this rho value changes, we see the randomization of this morphology as a function of the deposition conditions. So this was the major finding of this work, that you could change the direction of phase separation depending on the deposition conditions. So we saw this as a scientific challenge. Could we take this understanding and replicate it experimentally during PVD deposition? Could we heat the substrate and give it the deposition conditions needed to change the surface diffusion length to change the direction of phase separation? So our hypothesis here is that if we can control that diffusion length, we can control the direction of phase separation in these thin film morphologies. And I want to share with you the experimental methods we used to do this study. So we saw this equation here as a function of deposition conditions. So the two deposition conditions that feed into this equation are the deposition rate and the homologous temperature, which is the substrate temperature divided by the melting point of the material. And what we could use is deposit a matrix of sample to start seeing where those phase-separated morphologies fit on this morphology map. And so how we did that was we took this ideal copper moly phase diagram or material system, which is completely insoluble. We co-deposited it onto a heated substrate to force phase separation, and we subjected it to a slew of deposition conditions, or matrix of sample conditions, to start applying where those morphologies would fit on that morphology map. We use a characterization technique known as scanning transmission electron microscopy to measure or map out those phase boundaries and phase domains. So we see the atomic number using atomic number contrast imaging to measure the shape and the spacing of those domains. The chemical imaging can measure the chemistry of those domains. We can look at the interface between the two materials in high resolution to look at the structure and defects of that interface. And we can use electron diffraction to measure the crystallography and texture of the resultant films. So I've introduced that to you. So what did we actually get? And I'd like to share with you a summary of those thin film architectures that we designed using this process. So these are all atomic number contrast imaging, where we can see copper is darker in this sample, and brighter regions represent the moly-rich domains in the structure. You can see the length scale of these three morphologies and how the concentration is evolving as a function of the deposition conditions labeled here. So you don't have to take this all in because we'll describe them each in turn. So at the lowest deposition temperature that we deposited the sample at, we achieved vertical concentration modulations of copper and molybdenum. So this is two views of the sample, one in cross section and one in plan view or top down onto the film. And the film growth is indicated here in the cross section image. And what I can show you is that we have copper-rich and moly-rich domains stacked in a vertical direction in the sample. You can see them labeled here at a length scale of about 11 nanometers. And you can see this vertical stacking in the chemical mapping image in the inset up in the upper right. If we actually look into these two domains, what you can see is that there's actual lateral character to the copper and moly rich domains that extend into the thickness of each of those layers. What's really interesting about this sample is that if we measure the crystallography, we only pick up frequencies from the body-centered cubic crystal structure, which is represented by moly, which is the equilibrium moly crystal structure. But if you know anything about bulk copper, the equilibrium crystal structure is actually face-centered cubic crystal structure. So what we have here is actually a metastable copper layer adjoined with coherent with the BCC moly-rich layer. And I'll show you that in detail in just a second. In plan view, when we look at the sample from top down, you can see these tortuous-like morphology into the thickness of the film with copper and moly-rich domains. And if we actually look at the interface between those two crystals in high resolution, you can see that copper is actually strained to match the lattice parameter of moly into a BCC crystal structure, forming a coherent interface between the two crystals. So in summary, what we have is a crystallographically coherent, chemically separated vertical design of the material. At slightly higher temperature, we actually change the direction of phase separation 90 degrees into lateral concentration modulations of copper and molybdenum. You can see that here in the chemical imaging in an approximate length scale of 7 nanometers. If we take a look at the crystallography of the sample, what we see is actually the two equilibrium crystal structures for both of the constituents, both face FCC copper and BCC moly in the crystal, or in this film, when we look at the film in top down. We can actually pick out frequencies in that crystal structure, or in the crystallography measurement, and see that this film is highly textured when we pick out one of those peaks and measure the sample at dark field TEM. If we look more closely at the interface between the BCC moly and FCC copper, you can actually see that this forms a semi-coherent interface between the two crystals, and it has a Kerjman-Sachs orientation relationship. An orientation relationship describes how two crystals are aligned with one another. In fact, it describes a set of parallel planes and parallel directions. And here's what that looks like schematically, where we've matched up body-centered and face-centered cubic material at the interface. And what's really interesting about this structure is that we have misfit dislocations that literally interface and actually provide for the mechanical performance, or describe some of the mechanical performance we see in this material. You can see those misfit dislocations described here. And so what we have in summary at this temperature and deposition condition is we have a crystallographically semi-coherent, chemically separated lateral design. At the high temperature, you can see where this is going. We actually have a randomization of those phases in both cross-section and in plan view. And we can see we have a much more random crystal grain orientation in the sample. We've lost some texture. We have a much more tortuous bicontinuous-like morphology in both of those views of the sample. So here we have a random design in the morphology. So in summary, here are those three morphologies. And so we wanted to match up our empirical results to the analytical model put forth by Dr. Michael Betzman's group. So what we did is we saw this relationship once again, and it describes the domain size proportional to the square root of 1 over the deposition rate. So we tried to map out, again, that R value, or concentration modulation, as a function of the square root of 1 over domain size, or deposition rate. And we saw that our experimental results actually match well with what was predicted by this model. And so, and experimentally, we can show that here, is that at a particular temperature, 800 degrees C, by increasing the deposition rate, we can actually refine the structure in the sample. So we can see that our model, or this model, actually describes our system and our empirical results. So what we, in conclusion, through the PVD conditions, we can actually control the direction of phase separation by controlling that diffusion length in the sample during deposition. And so if you come to me and want to design your material in a very specific way, the next challenge we saw is, can we develop some sort of predictive control over these morphologies? Could I tell you the deposition conditions you need to design your material in a very specific way? So our hypothesis is that by understanding how the deposition conditions play into that diffusion length, we can start to predict these phase-separated morphologies. So starting with this equation here, we actually, in matching it up with our empirical results, the Yunzi-Wang group at Ohio State actually put forth a morphology map based on their phase field simulation that describes the phase fraction of the material against a normalized deposition rate. Now don't let that confuse you, that's just the inverse of the surface diffusion length proposed by Dr. Betzman's group. So our material actually has equal amounts of the two materials, so 50% fraction. And you can see that depending on the surface diffusion length, you can actually change the direction of phase separation using those deposition conditions. And so what I'd like to describe is each of those morphologies in turn and how they develop. So first off is the LCM phase separated morphology, and that is when we have a high surface diffusion length. What's happening here is that the rate of phase separation is much greater than the deposition rate. And I wish I could show you the video, of course it's not working, but what you would see in the video, I don't think it'll work, is as the sample is being deposited, an equal amount of yellow and blue atoms that deposit onto the substrate, they have enough time to diffuse and to phase separate before the next layer arrives. And the next layer that arrives, like atoms, have a simple job of just finding regions of like phase underneath, and they build up into this LCM-like morphology you can see schematically in this corner. Now, at slightly lower diffusion length, we see a transition in phase separation direction to the VCM structure. What's happening here is that the rate of phase separation is roughly equivalent to the deposition rate. And so looking at that more closely, what we predict is happening is this is describing increasing film thickness as you go down the page here. And in the first few layers of deposition, the system tries to phase separate into these red and blue rich regions. Unfortunately, by the time the next layer arrives on the substrate, that underlying layer hasn't reached terminal composition or fully demixed on the surface or on the substrate. And so that first layer starts stealing like atoms from that second layer, forming a chessboard or checkerboard-like structure. Surface energy arguments actually start to then interconnect those phase-separated domains, and you can see that at later stages in deposition, we have a VCM-like morphology at lower diffusion length. But one thing you might notice is that our empirical results, based on the diffusion length, actually predict random concentration modulations at the highest diffusion lengths during deposition. But our morphology map only predicts 2 of those morphologies. So we can put the VCM and the LCM on there, but our empirical results suggest that the RCM should be to the left in that plot. And so this model doesn't actually predict that RCM-like structure. And what's happening here is that RCM structure is inherently 3-dimensional. This morphology map was done by a 2D phase field simulation. So we extended our model in 3 dimensions in phase field to actually form or predict this RCM-like morphology. So here's our results of our phase field simulation. And what you can see here is that the system tries at a high temperature, tries to form this LCM-like morphology. But at this higher temperature, we've actually activated bulk diffusion. And that bulk diffusion leads to the breakup of the LCM-like morphology to a much random interconnected like structure we saw in experiment. And so we actually were able to form a 3D morphology map. You can see plotted here, which predicts the RCM-like morphology. You can see the regions of those morphologies labeled here. And we actually applied all of our empirical results onto our own morphology map, which is a function of deposition rate and deposition temperature. You can see those morphologies labeled here. And our results actually match up very, very well. If you just follow at one deposition rate, increasing the temperature, which increases the mobility of the constituents, you can actually see agreement with our empirical results or experimental results. Now this plot was only made for a certain set of mobilities, but we actually phase simulated morphologies or mobilities much greater than that, which actually predicts this RCM structure. It's just not included in this plot. So the second conclusion we can make is that we've been able to improve the model for phase separating within films and design some sort of predictive control over the interface morphology. One thing I've kind of been hiding from you on this experimental morphology map is that we see a completely different morphology at the lowest deposition rates we experimented with in this study. You can see that it's actually not a homogeneous-like morphology, but in fact hierarchical or heterogeneous. And that's where I want to go next. It's actually a phase-separated structure that has multiple lengths or multiple scales of phase separation during deposition. We actually dub these composites of composites. But if you look at our model, it doesn't actually predict the structure or a hierarchical-like morphology based on the deposition conditions. So we ask the question, how do we account for these structures? And that's where I'd like to go to next, is describing these hierarchical phase separation during deposition. Here's a summary of those results. And what I really want to stress is that we're only depositing 2 materials here, but what's interesting is that we have 4 different crystal structures, some of which are actually metastable or pseudomorphic. We can actually see a transition in morphology based on the deposition condition. Now, these were all deposited at low material flux, and I'd like to describe them to you today in turn. So at the lowest deposition rate we experimented, here is a high-level view of that sample in cross-section. At the sample deposited at 400 degrees C. And what I'd like to point out to you here is before we could describe those phase-separated like morphologies with 1 length scale. Here, we can no longer do that. We have to describe them with at least 3. The first length scale, as you can hopefully see, are these dark regions scattered throughout a brighter matrix in the sample. And what these are actually single crystal copper islands, and they contain a little bit of FCC particles, which I'll describe to you in just a second. That brighter region you see in the sample is actually a bicontinuous morphology that's surrounding those copper islands. So that's lambda 1. What about lambda 2? If we actually blow up in higher resolution what's going on in at lambda 2, what you can see is this atomic number contrast image, which shows the copper matrix behind in dark. What we started to see is actually brighter regions in this image. And I can actually highlight them here with circles, and you can actually see that they're very ordered and arranged in a very particular way. We chemically mapped this region of the sample. We discovered that in fact it's moly precipitates that are arranged in a superlattice inside the material. We actually measure the crystallography of the high resolution image of the sample in fast Fourier transform. We can only pick up frequencies from the face-centered cubic crystal structure, which suggests to us that this whole matrix is actually FCC crystal structure, which actually, if you consider moly, is metastable. Moly would prefer to be in the BCC crystal structure. So what we have here is ordered FCC moly particles inside that copper domain. So what we have is single crystal copper domains containing that metastable or pseudomorphic FCC moly superlattice. At lambda 3, what we have is something that we're all familiar with now, is this LCM or lateral concentration modulations of copper and molybdenum at a small length scale. You can see that in the chemical imaging here. And the crystallography of this region of the sample is very interesting in that we actually, in this case, we have pseudomorphic copper. So whereas before in the islands we had pseudomorphic or metastable moly, here we have metastable copper in the BCC crystal structure in this matrix of copper and molybdenum. So in summary, we have a metastable chemically separated BCC copper, BCC moly in a coherent matrix. At slightly higher temperature, we actually coarsen the structure quite considerably. You can see lambda 1, these lambda values have increased. If we look inside of those islands, we still have a bicontinuous matrix with single crystals islands scattered throughout. If we look inside that island, we can actually see again those FCC moly particles scattered within that island, of that copper-rich island. You can see that they've lost some ordering inside that copper-rich island. So what we have is larger pseudomorphic FCC moly precipitates. The matrix is again an LCM-like morphology with lateral concentration modulations of copper and molybdenum as shown in this chemical map. By measuring the crystallography, we've achieved equilibrium copper and equilibrium moly. And if you actually look at the interface between those two crystals, you can see that we've again designed a semi-coherent interface between the two crystals in a Kürgemann-Sachs orientation relationship. So in here we have a highly textured FCC copper BCC moly matrix. At the highest temperature, you can see where this is going. We've coarsened the sample again quite considerably. What we can see is that we've actually designed moly particles inside of those islands that are the equilibrium crystal structure or body-centered cubic crystal for the moly particles. And again, the interface copper in a Kürgemann-Sachs orientation relationship. So here's again a summary of those results in schematic form. We apply them to our morphology map that we described before. But the scientific challenge is, can we develop some sort of predictive control? None of the models that we described before predict this sort of morphology. Neither the 2D phase field or the 3D phase field simulation that we did. Now, what's really interesting is that both of these models actually describe a single surface interdiffusion length, which is actually an average between the surface diffusion lengths of both of those constituents. But we hypothesize that we actually can't consider just the interdiffusion length. We have to consider the diffusion length for both of the constituent species. What do I mean by that? Is that we need to describe or consider the mobility difference between the two adatoms or two constituents to describe this morphology. What do I mean? Well, if you look at the mobility between copper and moly adatoms, you can see that copper is much more mobile than the molybdenum atoms at the temperatures that we deposited in this study. What that translates to is a diffusion distance much larger for the more mobile species, in this case copper, than molybdenum. And so schematically, what we think is going on is that at early stages of the deposition, you can see these two adatoms on the surface, one much more mobile than the other. As this structure starts to build up, we can see it attempts to form an LCM-like morphology or phase separate, but the copper adatoms can jump or travel much farther than those blue, slower mobile species. What starts to happen is that because the system prefers to demix, we have an agglomeration of copper in the structure, and any moly that gets deposited inside of that domain can't travel outside of it, and that's what we think is giving rise to those pseudomorphic moly precipitates inside the structure. what you can start to see is the development of a disparity in the phase fraction depending on the location inside the sample. Where one, we have a disparity in the amount of copper versus moly. The other, we develop these copper islands, where the phase fraction of the material we predict is much more close. We can see the development of a homogeneous morphology or an LCM morphology that we saw at higher deposition rate. So what we can conclude here is that, in the very least, we need to improve the models that we described before. We think we need to consider the mobility differences between the constituents during deposition. And so I've described many, many different morphologies so far to you today. As the name of the title of this talk suggests, we're interested in the mechanical performance of these films. So let's look at the performance. We wanted to consider two different extreme environments that we applied these materials to. The first being mechanical deformation. So these hard or tribological coatings are used in mechanical applications as protective coatings. So they need to be hard. And they're also used in nuclear radiation environments, such as this fusion reactor, as cladding inside of the nuclear reactor. So let's start off with the mechanical deformation. So we know how 2D material, or materials with 2D interfaces behave, like the one I imaged here. Under compression, they behave like a brittle material. All the plastic flow in the material localizes into a single shear band, and the material fails very suddenly. And because of flow localization. The scientific challenge here is, do bicontinuous interfaces, when we extend those interfaces in 3 dimensions, can they distribute strain much more uniformly? We have these types of morphologies that we can play with. Our hypothesis is that plastic flow is no longer confined in the sample, and the sample can be much more deformable. So my colleague Yushi Sui here at Michigan actually led a study where he compressed in a novel TEM experiment these 3 morphologies and gave us the resultant stress-strain curve for each of these morphologies. And you can see that labeled here. What I'd like to highlight is that the VCM structure actually behaved much like a multi-layer-like design, which has high strength but limited deformability. The LCM morphology actually had enhanced deformability due to the presence of semi-coherent interfaces. And finally, the random concentration modulated sample actually had an excellent combination of both high flow strength, and plastic deformability. So the conclusion here that we can make is that bicontinuous copper moly structures prove to be both strong and plastically deformable in compression. How did the hierarchical morphologies behave? Very similarly. We've actually compared the multi-layer design to a hierarchical-like morphology. In this case, the sample deposited at 400 degrees C. And we saw that the sample in the multi-layer copper moly system actually loaded to 2.8 gigapascals, but failed suddenly due to shear banding in the material. You can see that using this TEM image of the sample here. The hierarchical morphology actually strain hardened at high strain rates and distribute plastic strain much more uniformly, and we didn't see examples of shear banding after compression. And the other environment, so that's mechanical behavior of the sample. Nuclear radiation is actually an important aspect that uses environment that uses thin films in the application. And so in neutron irradiation, such as in a fusion reactor, materials behave very interestingly, and that when they're struck by a high energy neutron, we actually have a cascade of damage that occurs inside of the material. We can have defects such as interstitials and voids, and actually the creation through nuclear transmutation of helium inside the metallic sample. Now, helium is completely insoluble with any metal. And so what happens is we start to actually develop porosity inside the sample as the irradiation dose increases. So take this fully dense tungsten sample here. As we hit it with neutron irradiation, the sample actually develops pores throughout the tungsten material. And we dub this tungsten fuzz because it develops into this porous-like structure. And this material is actually the embrittlement, or the structure embrittles at high irradiation dose. And that becomes a problem if we're using these types of materials in a fusion reactor or nuclear application. So we observe this helium that gets trapped inside of the metal and eventually embrittles the material and it fails. So the scientific challenge here is, how can we manage deleterious helium that gets trapped inside the material. And so you could possibly think of two approaches to solve this problem. One approach might be to confine helium in very specific locations inside the sample. This multi-layer design, like I described before, actually if we interface a BCC and FCC material, we create misfit dislocations across the interface. And these are very useful in terms of helium entrapment, as helium atoms like to diffuse to that location at the interface. We can actually see this simulated model where we implant helium inside the sample. It diffuses to the interface, and those misfit dislocations act as traps between those two layers. We've actually seen this experimentally. This is a copper niobium multilayer. You can see the development of helium bubbles inside the sample due to helium production. And this green plot actually measures the density or the accumulation of helium across the thickness of the sample. You can see that it's the helium density is much greater at the interface as opposed to the thickness of each of those layers. But what if, instead of confining the helium at the interface, what if we were allowed to what if we could flush it out during irradiation? What if we could, instead of confining it at the interfaces, we could just let it escape outside the surface? That would put an upper limit to how embrittled the material can become. And so recent studies actually concluded that if you can design interfaces very specifically, you could actually develop nanochannels of helium bubbles at an interface, and if those interfaces extend to the surface of the material, that helium could be flushed out at the surface. Well, we have very interesting structures that do have interfaces that extend in 3 dimensions to the surface. And so we asked the question, well, what if we were able to implant these samples with helium and see if there was a development of nanochannels to allow for the escape of helium in a nuclear environment? Our hypothesis being is that these bicontinuous interfaces that extend to the surface can facilitate helium escape through the surface. And so what we did is we simulated a neutron irradiation environment by implanting helium into these 3 different structures at a certain energy and temperature and a range of fluences of helium ions. And I want to describe to you one of the results in the structure. So this is actually the bicontinuous structure, and I've actually blown up this image here in bright field. And what I can, hopefully you can see, is that the structure is littered with helium bubbles inside the structure, but the helium bubbles, as pointed out by these pink arrows, inside the blue moly-rich and copper-rich domains, actually confine themselves to the FCC-BCC interface. And so what we have is that these helium bubbles do behave like inside the copper multi-layer design, and confine themselves to the helium, to the interface. And if we actually map out helium retention in the sample as a function of dose or fluence, we can actually see that we have allowed some of the helium to escape through the material surface. Now here's a plot of helium retention, so how much helium is being contained inside the sample as a function of fluence, so how much helium we're actually implanting inside the sample. The black line represents a material where all the helium that gets implanted gets contained and confined inside the sample. The other colored lines actually represent our morphologies. What I hope you can see here is that the LCM and RCM morphologies actually allow for some of the helium to escape at high fluences. You can see as we increase the fluence, that retention of helium inside the sample starts to decrease. So what we think is happening is that, and these are the representative morphologies, what we think is happening is that bicontinuous interfaces actually allow for helium to diffuse along the phase boundaries and escape from the interface at the surface. So I've described to you a lot of different topics today, and what I'd like to do is just describe a summary of those results. So first thing is that synthesis physics, we actually were able to control the direction of phase separation by manipulating the diffusion length during deposition. We developed predictive control over the morphology by extending our model in 3 dimensions, our phase field simulation in 3 dimensions. What I didn't show in this work is that we actually developed a new deposition technique known as high PIMS to control the morphology even further. We designed these hierarchical novel materials where we have phase separation happening at different length scales in the sample. We tested the mechanical response by deforming these samples inside the TEM and seeing how they behave, and they film much more uniformly. And we experimented with implanting these samples and exposing them to irradiation and seeing how they retain helium inside the sample. So we did a whole slew of different experiments in this work, but I'd like to share with you or stress that the impact of this work goes much beyond just thin film design. It can actually impact materials design across material science. We can actually use these results in bulk materials to improve the design of materials and improve their performance in various applications. So I'd like to point to you the publications that we have on this work and tell you to please read them and for more information. And I couldn't be standing up here today if I wasn't standing on the shoulders of other people. All of you in this room, of course, and specifically who funded me. So NSF, the DEMREF program, and the CRED specifically. And I'd like to specifically thank my committee members for being here and listening to my work and evaluating my work. And of course, all of the collaborations, both here at the university and across the country at different institutions. I specifically like to thank the staff at MC Squared that helped me with the microscopy in this work, and the Center for Integrated Nanotechnologies at Los Alamos that I did a good portion of this work that I showed you today. And of course, I would never be standing up here without the help of the MSc department. Some of you in the room, specifically, I'd like to thank Renee. She is invaluable to this department, and you all know, the students in the room, how valuable she is. And of course, all of the staff that support and make sure this machine runs on time. So, and I'd like to thank them specifically. So, I'd like to thank Professor Misra very specifically. This group of people is great, and he's the leader of that group of people, and he has taught me over these 4.5 years how to be a good researcher. I hope you can see that, and how to be a good leader in this department. And I specifically thank him for that. And we do have fun in our group. So I'd like to show you that image there. I'd like to thank my friends for all the good times that we had throughout my time here. Here are just some of the images of all that we did together. You know, the PhD is a lot of work, but we have a little bit of fun too. And I specifically thank you for that. And of course, my family at TRI, they supported. They were friendly to me, helped me, and made my journey here much more enjoyable. And of course, my family, all these pictures here, just for their selfless love and support throughout these last 4 years. And I couldn't say goodbye without at least embarrassing her a little bit. So I'd like to thank Sydney for bringing me through the end of graduate school. And with that, I'd like to conclude my talk, and I appreciate any questions. Thank you.
Okay, thank you for that amazing blue talk. Questions from the audience?
So basically at these different rates, you get sort of some metastable states. And you say you actually have an amorphous copper state in the first material?
There's not amorphous state,
Oh,
but it does have a BCC crystal structure at the lowest temperatures that we deposited at.
So if you take one of those materials that does have one of these metastable kind of kinetically trapped states, would you expect that under like lots of cycling and compression that you might actually see a shift in that structure, or would it be pretty stable?
That's a great question. We haven't done those experiments yet, obviously. There is suggestion that if we were to load these structures that, for example, the molybdenum might transform into a different crystal structure under high pressures. But yeah, that's an interesting thought that we could look at the mechanical stability of these samples under compression.
Another thing then, given that you probably need to take in the diffusion coefficients for both components that are pretty different to sort of model those dynamics in the heterogeneous system as well. Did you ever radiate the deposition rate of those two things to kind of maybe get at that? We can say, well, we can model it, more like component one and more like component two, or do you really have control over those deposition rates individually, or?
You actually jumped the gun. We're trying to do that right now. So we're trying to see if but if we can change the diffusivity of those constituents based on the deposition rate. Yeah, so here I just showed you results for 2 different deposition rates. Now we're limited to range of deposition rates with which drugs. But yeah, we can play with that aspect of the deposition to play with those parameters.
Questions here?
So obviously you said that the main thing was you wanted insoluble binary system. But what specifically made you choose copper? There are obviously other binary systems that are very insoluble.
Yeah, that's a great question. So that was just our model system because across temperature and composition at high temperatures it's completely immiscible. We're actually doing experiments now that if you change the system, basically changing the thermodynamics, do those systems behave similarly? So we just chose that model system for these experiments, but we're trying to compare them with other systems. But like you said, if they're miscible, they hopefully behave very similarly. We expect them to behave similarly at different deposition conditions.
For the mechanical deformation of the 3 LCM, VCM, and RCM, why do you think the RCM had lower true stress in comparison to the other 2?
Yeah, that's a great question. So we actually, the LCM morphology actually had kink banding form during deformation, and because of the lateral domains of the sample, which behave very similarly to multilayers, we formed some kink bands in that structure in previous experiments. And so because these interfaces are now bicontinuous, they have a much more uniform deformation under compression. I think just the design of the domains contributed to that.
Speaking of other systems, so you noted that the hierarchical structure was present in copper moly. Would you predict it for any other of the systems, and then why or how would you be able to know that?
Yeah, that's a great question. So we've experimented with copper iron, which is also an immiscible system, and it behaves. Our initial results suggest that it behaves very similarly, but in a different set of deposition conditions. So depending on how insoluble the system is, and where you see the immiscibility, you can actually deposit those same morphologies. Does that answer your question?
Sure, but of the hierarchical structure specifically?
Oh, the hierarchical structures. Yeah, so what we predict is that if, like in the copper moly case, under certain conditions, if the mobility or surface diffusion length difference between the 2 constituents is large, we might be able to see that hierarchical morphology. So we actually published a work with copper tantalum that shows a very similar morphology progression. Yeah, which has a very disparate mobility between the constituents.
So a major factor in your work is temperature. So how might that kind of play along with mechanical or nuclear deformation? And could that help or hurt the moving of the materials and atoms? And could the increase in temperature also help the escape of the helium from the materials?
Yeah, so you're specifically asking about the temperature during deformation or radiation. Yeah, so we don't exactly know the effects of temperatures, but what we expect is that the diffusion of helium in the sample would increase as a function of temperature, with added temperature. So we don't actually know how that would enhance or detract from the escape of helium, but we know that it would enhance the diffusion of helium inside the sample. So we might expect that the confinement of the interface happens much sooner, and the development, if there is development of nanochannels, that happens sooner at higher temperature.
Like, so you have like the set model, you're seeing atoms pop onto the sample over a certain period of time, and at the end they form these accretive structures. Like, is there any way to look at that as it's happening? It's would that be I assume that probably would do, but is there any method to build it instead of looking at the sample after you're done?
Yeah, that's a great question. So we're limited into what we can see in terms of morphology development. I don't know of any technique that we could put inside the chamber to see that as the film grows. We can get crystallography information through diffraction inside the chamber. As far as I know, we're limited to just seeing what the crystal structure is during the development of the film. possibly what we could do, and we've played with this idea, is to deposit, say, an amorphous film of these two constituents, heat it up during deposition, or excuse me, during TEM imaging. So we can actually have a heat holder inside the TEM where we can apply those thin films and possibly see the progression of phase separation. But during deposition, I don't know of any technique that we can use to do that. But that would be cool. Yeah.
I was going to ask, in terms of characterizing the helium, do you have, kind of ideas? Is it just basically kinetically trapped? Does you have some binding and some structure within the helium, or is it basically just kind of kinetically trapped and behaving like a gas, or is it kind of ordering itself into the structure?
Yeah. So once helium is produced inside the sample, it's very much attracted to voids that are also created through radiation. And so those helium try to find those voids, and the helium does behave like a gas, and so it doesn't like to be in the material, but it is trapped. It's a gaseous structure inside the metal, and so that those helium atoms do build up into bubbles and start to actually create blisters in the sample once they try to erupt from the surface. And that's what impervious the material.
And so they essentially, when it gets brittle, you're saying that you're getting some pockets of probably pretty pressurized helium in the material. Do you have any idea, or anybody have any idea what those pressures are locally for the helium, or just before it breaks?
Yeah, that's a great question. It's definitely information out there, but I don't know about it.
Yeah, the two more questions, John.
How did you detect?
So this was a process known as NRA, or nuclear resonance analysis, I believe, is the R. I can't remember exactly what the R stands for, but it measures after we've implanted the sample how much helium is retained. So this was done by collaborators. I'll have to look exactly at the specifics how they did that, but.
So I was curious, you have these tiny bubbles that look like they sort of nanometer dimension at the interfaces. I just wondered how you knew for sure because the helium, those STEM images, so you just going by the contrast or what?
Those are where I showed the bubbles inside the structure. Those are bright field TEM images. So by Fresnel contrast, we can see that we predict that the contrast changes when there were bubbles in the structure.
Somebody else.
I actually have the same question.
So if you're changing the substrate itself, are there any effects from starting roughness or surface energy?
Yeah, that's a great question. We only used one substrate in this study, but we suspect that by changing the surface energy of the substrate, we could potentially change the initial structure of the phase separated morphology. Yeah, we'd have to just see what the difference in surface energy would be between depositing film and the substrate.
Oh, thank you for your participation and your questions. Any questions from the staff? See staff, or so many of you showed up with hands. A big round of applause for all the staff. And the family who came from New York and all over the place. Thank you so much. Okay, we'll take a short break and then the committee will reconvene. The rest of you are free to go.
Oh, nice to walk tattoos.
Thank you. Yeah, I'll tell you what. Hello, Sherry.
Okay. But you are not Japanese, is that right? Oh.
Yeah, this is based off of my back.
Oh, okay. What is that?
Yeah.
So you can close it off. God of Thunder. Oh, okay. Yeah. Cool.